property. Macroscopic properties. Macro means large. Micro means very small, right? Micro means very small and macro means large, bulk properties. The properties which are bulk, okay, which can be seen by a naked eyes. You can see the naked eye by your naked eye, and you can see and you can observe the changes, what is happening. So the equilibrium is a state where there is no apparent change in the macroscopic properties of a system. So that's how you can define the equilibrium. Other ways, by other definition, you can write down equilibrium is a state where the rate of forward reaction and the rate of backward reaction becomes equal. The rate of forward reaction and the rate of backward reaction becomes equal. Now, what does this statement mean? The rate of forward reaction is equals to the rate of backward reaction. Now, see, suppose we have a reaction, H2O. Okay, water, first it is in liquid state. Water is in liquid state. यहाँ पे क्या हो रहा है? Physical transformation. Physical transformation, the phase of this, the state of this water is changing from the liquid to the gaseous. The gases means here the vaporization is being happening. क्या हो रहा है यहाँ पे? Vaporization. The liquid is getting converted into a gas. Okay. So if I say H2O, this is a liquid, it is getting converted into a gas. So this arrow, this tells us about the forward reaction. The reaction occurs in a forward direction. Liquid किसमें change हो रही है? Gas में. But this is a reversible process. This is a reversible process. This gas can also convert it into a liquid. Okay, and this reaction is known as, this is a backward reaction. ये क्या हो रहा है? Again, the gas will get converted into a liquid. This is a backward reaction. So at equilibrium, when there is some reaction and that reaction is in equilibrium. So what does this mean? The rate of forward reaction is equals to the rate of backward reaction. So the rate of forward reaction, the rate of the conversion of liquid into a gas in this equation, okay, is equal to the rate of conversion of gas to a liquid, means the rate of backward reaction. And how we can show that? RF, the rate of forward reaction, is equals to the rate of backward reaction. Clear, everyone?
Yeah, ma'am.
Yes, ma'am.
Now, now let's see what are the types of equilibrium. So there are three types of equilibrium which exist. First one is your physical equilibrium. Second one is your chemical equilibrium, and the third one is your ionic equilibrium. Okay, so we will see each and every type of equilibrium in details. So first one, physical equilibrium. Physical physical equilibrium. So what does this mean? Physical equilibrium means, so in physical equilibrium are those type of equilibrium in which the amount it does not change. Whatever the amount you are just taking, it will be as it is. Okay, the amount will of the substance will not change. Only the phase, the state will change. If it is in liquid, so it will get converted into a vapor, gas, solid into liquid, etc., etc. So only the conversion, the phase changes, only the state of a substance changes in the physical equilibrium. So that is known as physical equilibrium. Those equilibrium in which the phase changes, the state changes. Okay, the amount of liquid. So for example, again, let's consider this water. So water, it is in liquid form. So it is getting converted into a gas. Okay, so again, you can see this is a forward reaction, and this is the backward reaction. Okay, and if I say this reaction is in equilibrium, so it means that the rate of forward reaction will equals to the rate of backward reaction, right? And here you can see, because this is a physical equilibrium, so the amount, suppose I play to 10 ml. So 10 ml will be as it is. You will get a 10 ml of gas also. So the amount of liquid is always equals to the amount of vapor in the physical equilibrium. The amount will not change. Okay, there will be no interruption in the amount of a substance. So it will be as it is, only the phase change. You can see liquid is getting converted into a vapor. So only the phase changes, but the amount is fixed, amount is constant. So that is the physical equilibrium. Suppose we have a solid, okay? Suppose solid to liquid may change, or there is a fusion. The reaction type is fusion type of reaction. So here, the solid is getting converted into a liquid, right? Only the state of a substance is getting changed, not the amount. So amount of solid and liquid is constant here because this is a physical type of equilibrium. Next example, देखो, solid is getting converted into a gas. Which reaction is this? Sublimation. Here, this process is known as sublimation, right? So you can see the solid is getting converted into a gas. So the amount of solid and gas will remain same. Okay, will be constant. Next one, if you take the solute, okay, and solute particles is in solid form. Okay, and this solute is getting converted into a solute gas. Gas में convert हो रहा है, तो this is again a physical equilibrium. Okay, so equilibrium exists and the amount of solute which is in solid is equals to basically is equals to the amount of gas. It will not change. Only the phase will change. Right, so that's all about the physical equilibrium. And what about this arrow? What about this arrow? Why I showed this arrow? So this arrow, this half, this is a double half arrows. What does it indicate? It indicates that the process is in both direction. Both direction of process is going on means on the forward direction as well as in the backward direction. Okay, the reaction is same. Liquid is getting converted into a gas, and the gas is getting converted into a liquid. So this arrow you will represent it in a equilibrium chapter, right? So what it does indicate, it indicates that the reaction is going on in both the direction. It just shows the direction of the reaction, right? So this reaction basically it tells us about the forward reaction, and this one is your backward reaction. Okay, now you can write down. Now you can write down. Just note it down and let me know. Yes, written everyone. Can I scroll down?
Yeah, ma'am.
Done everyone? Written?
Ma'am, can you give an example for the D1 solute solid to solute gas? Like instead of water, another example?
Okay, instead of water, I can. Okay, suppose we just take, because you know very well what is sublimation process. What is sublimation process, Zunera? Yes. Who asked me the question?
Change, change of gases, like from
Change of gases.
different state.
Change of gases, are you sure?
Change of states, ma'am.
Change of states from which to which? The substance is converted from which state to which state?
From
Formation
solid to
process.
gas.
From solid to gas. Yes, very good. Okay, so just take any solid. Any solid. Suppose, say, what happens? Again, example of water ka le sakte ho, just a ice. Just take the ice. It is a solid water. Water is ice. Okay, and just a second. Just let's draw the, yeah, and it's converting, basically the sublimation process is going on. So this solid ice, okay, it is directly converted to a gaseous state. Vaporization ho raha hai yahan pe directly. Okay, the sublimation process is going on. So H2O gas, okay, vapors will convert her. So this is a example. Here you can see the solid is being converted directly into a gas. Okay, so intermediate state नहीं हो रहा, liquid में convert नहीं हो रहा, it just directly it converted into a gas. So there might be might required a high temperature. यहाँ पे बहुत ही high temperature पे होता है the sublimation process. So in that sublimation process, the solid ice is getting converted into a vapors. So that is example.
Okay, ma'am.
Only we have to see the physical state. What is equilibrium? Physical equilibrium. So in physical equilibrium, only phase change. Phase will change. The amount will be as it is. Whatever amount you are just taking in the reaction, it will be as it is. The amount of your reactant is equals to the amount of the product. It will not change in a physical equilibrium. Okay, Zunaira?
Yes, okay, ma'am. Thank you.
Okay, so the next thing, yeah, let's do this question. Okay, so what is this question? So a liquid is in equilibrium, okay, with its vapor in a sealed container at a fixed temperature. Okay, so what does question says? Question says that there is a container. Suppose this is a container, right? And in this container, a liquid is in a equilibrium with its vapor. Means H2O, which is in liquid, it's in equilibrium with the vapors, with its vapors. So that will be the reaction. Okay. Now this is a container and the temperature is constant. Temperature is constant. So what happens? There will be a liquid, okay, liquid, and it's being यहाँ पे evaporation processes is going on. Liquid is being converted into a gases, and both are in equilibrium. Liquid is in equilibrium with the vapors. This container में there will be a vapors as well as the liquid water. Okay. Now next. And then the volume of the container is suddenly increased. What happens? Suddenly, the volume of the container is increasing. So this was the initial. Okay. So I क्या कह रहा है in the first state? See this. A liquid is in equilibrium with its vapor in a sealed container. Okay. It means that here the evaporation process is going on as well as the condensation process. So, and the rate of, you can see this is the reaction. Okay, the liquid is being converted into a gases. So this is your evaporation process. Okay, so here you will talk about the rate of evaporation. The rate of evaporation, and this gases will convert it into a liquid. Okay, so this process is known as condensation. So here at equilibrium, you know very well, the rate of forward reaction is equals to the rate of backward reaction, right? And here the rate of forward reaction is equals to the rate of evaporation, right? Liquid is being converted into a gases. So यहाँ पे evaporation हो रहा है, vaporization हो रहा है. So RE, okay, will be equals to the RC. Okay, initially The liquid is in equilibrium with its vapor in a sealed container. So according to the question, it means that. So liquid, it's in gaseous phase, it's in equilibrium. Now, after some time, what happens? What happens? The volume of the container increases. Volume of the container increases. Now, what does this mean? What does this mean? So, volume increase over a container. The volume of the container is being suddenly increased. Okay. So, how it being increased? It was first initially it was in equilibrium. Means the rate of forward reaction is equal to the rate of backward reaction. Rate of evaporation is equal to the rate of condensation. Now, how the volume increases? Because the temperature is fixed. So, if the volume is increasing, see, we know that according to the according to the ideal gas equation, PV equals to nRT. PV equals to nRT. So, from here, P is equals to nRT upon V. What is the relationship between the pressure and the volume? The volume, basically, these all three are constant. Temperature is constant, gas constant, it is again a constant, and the number of moles, Kv constant. Yeah. Suppose we're just talking for the 1 moles. So P, the pressure is inversely proportional to volume according to this equation. So if volume increases, pressure will decrease. You can see by this equation, we can say that pressure is inversely proportional to the volume. And here, because here the vapors are present, so we will talk about the vapor pressure, right? So because volume is increasing, volume क्या हो रहा है? Increase हो रहा है. So here the vapor pressure will decrease. Vapor pressure will decrease. Okay, this is a liquid. So what happens? Vapor pressure will decrease because according to the ideal gas equation, pressure has an inverse relationship within the volume. So if the volume increases, according to the question, volume increases, so the vapor pressure will decrease. We are just talking about the container. Okay, where the vapor pressure in the container will decrease. Okay, now the question is, first question, what is the initial effect of the change on vapor pressure? Okay, so initial effect क्या आ रहा है? The vapor pressure. First answer you can write. The vapor pressure decreases. Okay, and in the first equation आप यहाँ से लिख सकते. Just a second. From here, write down the answer. The answer number A, PV equals to nRT. Just elaborate this by using this equation. You can show that pressure has an inverse relationship between the volume. So the volume increases according to the question. So vapor pressure will decrease. So the effect of the change on vapor pressure is vapor pressure will decrease. Is it clear, the first one?
Yeah, mom.
Next question is, how do the rate of evaporation and condensation change initially? Change initially. Okay. So how do the rates of evaporation and condensation change initially? Now see, because vapor pressure क्या हो रहा है? It decreases. Okay. Now you know very well because the volume is being increases and the vapor pressure decreases. So vapor pressure decreases. So what happens? Here we are just talking about this condition. So the rate of condensation, see, this was at the equilibrium. The first condition, this first container was at the equilibrium. But in the second one, what happens? The volume increases. Volume increases and the vapor pressure decreases. So if the vapor pressure decreases, so you know very well here. So the gases will occupy. What happens? The gases will occupy all the spaces in the container. जितने spaces उसे मिलेगा, it will occupy that. It will occupy that. Just a second. Just a second. Okay, sorry. Okay, see the next thing. How do rates of evaporation and condensation change initially? So here you can see the volume increases, right? Volume increases and the vapor pressure is decreased. Vapor pressure suddenly decrease. Why decrease? Because the same number, you can see the same number of gas molecule. Okay, because it's a closed container. Okay, it's a closed container. So same number of gas molecules now occupy a larger volume leading to a fewer collision जिसकी वजह से collisions बहुत कम होंगे and you know very well due to that vapor pressure decreases. So you can see here because the gases molecules are more than the water molecules over here. Gases molecules are more than the water molecules. So according to this diagram you can say that the rate of condensation is less than the rate of evaporation. Okay, because the gas molecules are occupying a larger volume. These occupy a larger volume. And why it occupy a larger volume? Because the gases, the liquid is getting converted into gases more. Okay, the rate of reaction or the conversion of liquid to gas molecules is more faster as compared to the rate of conversion of the gases to a liquid. Means the conversion, the rate of condensation will be less than the rate of evaporation. Rate of evaporation ज़्यादा fast है, it is more, okay, it is more than that of the rate of condensation. So that's why the vapor pressure is decreased and the gas molecules are very far away from each other and they are occupying more space. They occupy a large number of space, okay, leading to a fewer collision between the walls of the container. So that's why the rate of evaporation is more. This is more, you can write. This is more and the rate of condensation is less. Okay, means gases, liquid may convert हो रहे हैं slowly, but the liquid is getting converted into a gas more faster. Is this point clear? Or is there any doubt?
No, ma'am.
Okay. So you can write here second. So what about the change? So the effect of no this one the second answer. Second answer में you can write the vapor pressure will decrease because it is inversely proportional to the volume. Volume increases, so the vapor pressure decreases. And in the second answer, write down the rate of condensation will decrease and the rate of evaporation will increase. Okay, who will tell me the last one? It is very simple. What happens when equilibrium is restored? First क्या था? Initially it was in equilibrium. After some time volume change हुआ, volume is being increased. It means there will be a disturbance in the equilibrium. Now it is not in the equilibrium. Okay, the liquid is not in the equilibrium with the vapor. Okay, between. And after some time again the reaction comes in the equilibrium. The equilibrium is restored finally. So when the equilibrium is restored finally, what will be the final vapor pressure? Who will tell me? Yes, Anidhi? Just think about it. What was the condition for the equilibrium? Sunera, Aisha, Aman, Neha, anyone? It's very simple. What happens when equilibrium is restored? What are the conditions for the equilibrium? RC is equals to the rate of backward reaction is equals to the rate of forward reaction. That is the condition for the equilibrium, right? Starting में क्या था? The rate of evaporation was equals to the rate of condensation, right? After some time, the volume is being increased, right? It means the rate of evaporation is increased. Rate of evaporation is greater than the rate of condensation. After some time, the reaction is happening again. The reaction proceed हो रहा है. After some time, again the equilibrium is restored. So what happens? What does this mean? When the equilibrium is restored, it means that rate of evaporation is equals to the rate of condensation at last. Okay. And what about the vapor pressure? So vapor pressure was same as initial. जो initially था vapor pressure, it will be as same as initial. You can write in your exam. Okay, so this was some conceptual type of question. So first, the equilibrium was maintained. Okay, after some time, the equilibrium got disturbed, and the rate of evaporation is greater than the rate of condensation, right? And after some time, again the equilibrium is restored. Is it clear? This question is clear,
Yes.
everyone?
Yeah, ma'am.
Yes.
Yes,
Okay.
ma'am.
Okay, next one. Next one is your reversible reaction. So what is the reversible reaction? The reversible reaction is that reaction in which product that are formed can also react with each other to form a reactant under suitable condition. Okay, so the reaction which can be reversible, which can be reversed, the product can again be reversed to a particular reactant. Suppose A plus B. A plus B, these two other reactants, they react with each other, okay, and they form C plus D. Okay, this is known as forward reaction. This is the arrow, and this shows that the reaction is proceeding in the forward direction. Now, what happens? C plus D, this C plus D again has the capability. This product can be react with each other at suitable condition, under suitable condition. Okay, and they can again dissociate, or some reaction will proceed over here, and they can also form A plus B, which is a reaction. Okay, and this reaction will be under backward reaction. This is known as backward direction. Okay, so this type of reaction in which the can form product which is formed in a reaction by a forward reaction can again react with each other to form a reaction under suitable conditions. So that is a reversible reaction. The reaction which can be reversed. Product can be reversed to the reactant, and reactants can form the product. So that is a reversible reaction. Now, at equilibrium, you should understand or you should memorize these two. This is very important. This is the backbone of the equilibrium. You should know. At equilibrium, rate of forward reaction is always equals to the rate of backward reaction. जब भी मैं कहूँ कि this reaction is in equilibrium, so you should know that the rate of forward reaction is always equals to the rate of backward reaction. First condition for the equilibrium. Second condition is that the concentration of reactants and the products become constant. If the reaction is in equilibrium, so the concentration of reactant as well as the product, they become constant. So these are the two conditions for the equilibrium. Clear to everyone?
Yes, ma'am.
Okay, if it is clear, then choose the correct option. A, B, C, D. A is RF, means the rate of forward reaction is equals to the rate of backward. Is the concentration of reactant is equals to the concentration of the product. C is concentration of the reactant and concentration of the product become constant, and D is all of the above. Aorta.
A and C.
A and C
Ma'am,
is the
all of
correct
the
option.
above, I think.
No, it's not all of the above. It's A and C. The reaction, the concentration of reactant is not equals to the concentration of the product. Okay, they become constant. The concentration of the reactant and product become constant. Okay, but they are not equal. Constant और equal में बहुत ही difference है. These are not same. So first option, your RF, the rate of forward reaction is equals to the rate of backward reaction, and your C option are correct. Okay, this is not correct. Don't be confused in that. Okay, now you can know reversible reaction, the definition part, and this question.
Could you scroll down a bit?
Yes, done.
And the question.
Okay, question. Okay. Okay, now see this. You have to choose the correct graphs for the equilibrium. Okay, you have to analyze which graph is correct. Okay, I will give you 1 to 2 minutes.
First,
Just only first one. Can be more than one.
the first and second, sorry, third.
First, one, third. Okay, let's check it one by one. Okay, so this is the rate versus time graph, right? Rate versus time graph. So you can see this the rate of backward reaction. The rate of backward reaction it increases, right? And the rate of forward reaction it decreases. At some time, it here at this point they merge. It means here at this point RF is equals to the RB. Okay, means they are at equilibrium. You have to keep in the mind these 2 points: the rate of forward reaction, the conditions, the two conditions for the equilibrium. Okay, either the rate of forward reaction is equals to the rate of backward reaction, or the concentration of your reactant and the product will be constant. These two things you have to keep in mind. So this will be correct, yes. Why this is correct? Because rate of forward reaction at this point is equals to the rate of backward reaction. This is clear? This graph, आपको graph को read करने आना चाहिए. Clear, everyone?
No, no.
No, ma'am? Who said no, ma'am? Okay, see. So this is again the rate versus time graph. Rate versus time graph. Now see the rate of backward reaction increase हो रहा है, right? At some time it becomes constant. It decreases as sometimes it becomes constant, right? But here यहाँ पे कोई merging नहीं हो रही. There is no merge. They don't merge over here. Okay. So how we can say that the rate of forward reaction is equals to the rate of backward reaction? right? We can't say the rate of, because we will discuss here in the rate versus time graph, we will check whether the rate of forward reaction is equals to the rate of backward reaction. And in the concentration versus time graph, we will check whether the concentration of the reactant and the product is constant or not, right? So in these three, we have to check RF is equals to RB. So here you can see the rate of forward reaction is greater than the rate of backward reaction, right? Rate of forward reaction ये यहाँ है, and the rate of backward reaction is here. So rate of forward reaction is greater than rate of backward reaction, means this is not a correct graph for the equilibrium. At equilibrium, this type of graph does not exist because first condition does not match. Okay, the rate of forward direction is equals to the rate of backward reaction. Second one is wrong graph. Now, third graph. So this is the concentration versus time graph. Concentration versus time graph. Okay, so for concentration versus time graph, we have to check the concentration of R and P. Okay, reactant and the product. Constant है या नहीं? So this is the product. Okay, this is the graph. Concentration increase. Okay, after some time it got uniform. Okay, now this concentration decrease after some time it got uniform. But before coming in the equilibrium, there should be a merging point. Okay, ये merge होना चाहिए, these two lines merge होना चाहिए. After merging they get into the equilibrium, but it's not happening over here, right? So it's not happening over here. So you can say that this is wrong graph. Okay, this is wrong graph, and here the R and P are not constant. Are not constant. You can say. Okay, for this one, this is again the wrong graph. This is not in the. Okay, so between these first, second, and third, only first graph is correct. Now, coming to the fourth graph. Okay, now check. This is the product. Okay, this is the reaction. Now check this. These are not equilibrium. After merging, this product increase हो रहा है. The concentration of product is increasing. The concentration of reactant decreasing. At this point, they merge. Means in equilibrium में तो आए. But after some time, the again the product will increase and it decrease. We are not seeing this type of graph. Like after merging, you will see this. Like curve के बाद you will see the straight line, exact straight line. It means after merging they become constant. Okay, they become constant. The concentration of reactant and product, okay, they become constant. So it's not happening. ये straight line नहीं है. This is a curved line, right? So this is incorrect graph, and you can write like R and P are not constant over here. Second condition is not satisfied. So again, this is the wrong graph. Okay, now fifth graph. Let's check it. The product, okay, the concentration of the product. Again, this is the concentration versus time graph. Product, it's increasing. Okay, the reactant concentration decreasing. At this point, they merge. Okay, यहाँ पे क्या हुआ? Same हुआ. The concentration becomes equal. And after some time, what happens? Again, they will increase, decrease, and after some time they they become constant. You can see this line, like they become constant. So means this is a equilibrium. This is a equilibrium graph. It is correct. This graph is correct. Because it is line. This line basically it shows the equilibrium. Okay, now sixth one. ये तो clear दिख रहा है. You can see this R P, okay, the product increased, this reactant decreased. Okay, here at this point, it is at equilibrium. Again, they become constant. Okay, so they become, it is not compulsory always, and it is not necessary that every time the concentration and the product becomes equal, right? Equal. So here the concentration becomes equal. Here the concentration becomes equal. Okay, and the concentration becomes equal. The R and P are is equals to P. Okay, and constant also. यहाँ पे क्या शो कर रहा है? These are constant. right? This line shows a constant. So this is again correct. So your graph first, your fifth graph and the sixth graph is correct. So you should know how to read the graph. Okay, if you know how to read the graph, so you can easily do the graph type of question. Okay, clear to everyone? If there is any doubt, you can ask. Any doubt?
No.
Okay, just draw quickly. Done? Can we move forward?
Um,
Okay. And so you can write down these conditions. These are the conditions. When the rate versus time graph is given, so you have to check this, whether the rate of forward reaction is equals to the rate of backward reaction or not. And if the concentration versus time graph is given in your exam, so you have to check whether the concentration of the reactant and product will be is constant or not. Okay. Next, write down the heading equilibrium constant. Equilibrium constant. Okay. So suppose we just take the general equation A plus B. Okay, A plus B, they combine and they just form C. Okay, just a general term. We are not supposing it as a equilibrium reaction. Okay, just a general reaction there. A plus B, it's just giving you a C. So here you know very well the rate of any reaction is directly proportional to the rate of collision. The rate of collision between the reactant. More the rate of collision between the reactant, more the rate of the whole reaction. So the rate of reaction, it depends on the rate of collision between the reactants. Okay, whether it's a gas molecules or anything. So rate of collision will depend. And the rate is again is also directly proportional to the number of moles. The number of moles. Okay, and the rate is inversely proportional to volume. Inversely proportional to volume. So if you combine this equation, suppose this is your second, this is your first, this is your third. So when you combine second and third equation, so you will get rate is directly proportional to mole upon volume. Mole upon volume. Okay, so by combining second and third equation. Okay, you just got mole upon the rate is directly proportional to mole upon volume. Now, who will tell me mole upon volume will give you which concentration term? Which concentration term is equals to the mole upon volume? किसका formula होता है? The number of moles per unit volume. Yes, anyone? Why are you guys way too
Molarity.
molarity? Yes, very good. It's molarity. So molarity is what? The number of moles per unit volume. So it is molarity. So can we write the rate? Rate basically, what is this? This is a concentration. Okay, mole upon volume is a concentration. So rate is directly proportional to concentration. So which type of concentration? Concentration should be in molarity. Concentration should be in molarity. Okay, so we can say that rate is directly proportional to concentration. How the rate of reaction depends on concentration? Directly proportional. Okay, so when the concentration increases, the rate will increase and vice versa. Okay, suppose we just take A. Okay, A है A किसमें convert हो रहा है P में. A is the reactant and P is the product over here. So how you will write on the rate equation? So rate is directly proportional to the concentration of the reactant. Okay, ये आपने chemical kinetics में पढ़ा होगा आपने. So rate is directly proportional to the concentration of the reactant. Okay, now suppose if we have two reactants, A plus B. So how we can write on the rate reaction? Rate is directly proportional to the concentration of A into concentration of B. Yeah. Now, if I say 2A, if I add a stoichiometric over here, a stoichiometric coefficient, okay, so 2A, when it combines, so it will give you a P product. So how you will write on the rate equation? So rate is directly proportional to A, okay, A concentration, and the power will become the stoichiometric. Whatever here, which is written, which is multiplied to this A reactant, you have to write it as a superscript. You will use this as a power. Okay, आप power कितना लिखोगे? So concentration of A raised to the power 2. Okay, if I say it's 3A, 3A is converted to a P. So how you will write on the rate equation? So rate is directly proportional to the concentration of A. It depends on the concentration of reactant only, right? So raised to the power 3. Whatever the coefficient over here is, you have to write down as a power. Okay, so when this proportionality sign will be removed, so you have to write K, constant, some constant term. Okay, and this K is known as rate constant. What is K? K is known as rate constant. So this is for the general equation, general reaction. Okay, we are not talking about now, till now, we are not talking about the equilibrium reaction. So this is for the general reaction, जो हमने chemical kinetics में पढ़ा था. Now what happens when the reaction is in equilibrium? Okay, when both the reaction is proceeding, forward reaction as well as the backward reaction. तब हम क्या करेंगे? Let's see that. Okay, say this. Suppose we have A. Okay, small a is a stoichiometric coefficient, right? It's multiplied by this A. The A is the reactant. Okay, A plus B. Okay, in the forward reaction, it's give you C plus DT. Okay, and a small a, small b, small c, small d are the stoichiometric coefficient of all the reactants. Okay, now if we have to write down the forward reaction rate of forward reaction. So you will only consider, basically, we are just talking about the rate of forward reaction. So rate of forward reaction rate, we will consider this only. Okay, this is forward reaction, CC plus DD. Okay, so how you will write on the rate reaction? So rate of forward reaction will be equals to, you know very well, rate reaction may we only write on the concentration of the reactants, right? So what are the reactants in the forward reaction? So in the forward reaction, the reactant is capital A. So concentration of capital A, concentration of capital B. Okay, whatever the coefficient over here is, you have to write down as a power. So A, small a as a power, and small b as a power of B concentration. So that is the rate equation. So basically we are not it is directly proportional. First we will write down the directly proportional. Then when you remove this proportionality sign, you have to write down some constant term. Okay, and for the rate of forward reaction, I will write Kf. Okay, what is Kf? So the proportionality sign. Sorry, proportionality is the rate constant. Okay, it's the rate constant of the forward reaction. Forward rate constant A, and B. Okay, so that's how it is, this equation. Similarly, for the backward reaction ke liye, it will be the reactant. The reactant will become this. This will be the reactant, right? And what will be the product? Product will be AA plus BB. Just opposite to jayega in the backward direction. For the backward reaction, you will consider C and D as a reactant. These as a reactant. ये reactants हो जाएंगे for the backward reaction and these become the product. Okay. So for the rate of backward reaction, what will be the equation? So RB, rate of backward reaction, is equals to the rate constant for the backward reaction. So इसके लिए मैंने K भी लिखा है. The concentration of the reactant C, okay, raised to the power small c, concentration of D raised to the power small d. Okay, till here is it clear?
Yes.
Okay. Now we know that at equilibrium, the rate of forward reaction is equals to the rate of backward reaction. Okay. Now just suppose question one. No need to consider the question one. Just substitute the value. Okay, substitute the value. We know that at equilibrium, RF is equals to RB. Okay, the rate of forward reaction is equals to the rate of backward reaction. Now substitute the value. What is the rate of forward reaction? Kf, concentration of A raised to the power A, concentration of B raised to the power B. Okay, it will become equals to the rate of backward reaction. What is the value for rate of backward reaction? AB multiplied by concentration of C raised to the power C, concentration of D raised to the power D. Okay, now, so let's take this here. Kf divided by Kb will be equals to concentration of C raised to the power C multiplied by the concentration of D raised to the power upon. Okay, just take this here on the right side of this equals. Okay, so A, concentration of A raised to the power A, concentration of B raised to the power. Okay, now see Kf, the rate of forward reaction, the constant of the rate of forward reaction upon Kb will be equals to the Kc. We can say that Kc is equals to Kf upon Kb. Okay, so what is Kc? Kc is the equilibrium constant. Okay, so commonly we take Kf upon Kb, the ratio of these two, as a equilibrium constant, right? So you can substitute this by Kc is equals to, okay, all this term, the concentration of C, capital C raised to the power small c, concentration of D raised to the power D, upon the concentration of A raised to the power A, concentration of B raised to the, and this equation is known as equilibrium equation. Equilibrium equation. Okay, and what is Kc over here? So Kc is the equilibrium constant. Kc is the equilibrium constant. So here you can write down concentration of A, concentration of B, C, and D. All these are the equilibrium concentrations. And what is Kc over here? Kc is the equilibrium constant. These are the equilibrium concentration and Kc is known as equilibrium constant. Clear to everyone?
Yes.
Okay. So these are the concentration. If I say all the species are gases. So for gases, we don't take the concentration term. We just talk about the pressure. Okay, gases की अगर हम बात करेंगे तो gases के बारे में, so we will consider the pressure of that. Okay, pressure of the reactant and pressure and so on. So this equation, this equilibrium equation will become this. So you will not consider the concentration. So instead of concentration, you will write Kp. What is Kp? So the concentration equilibrium constant of gases. Okay, equilibrium constant of gas. So gases के लिए हम P लिखते हैं for the. So here this C refers to the concentration, right? And this is equilibrium. This equation, this constant is known as equilibrium constant, and P refers to the pressure. So we just when we use this equation for the gas species, so we just write Kp is equals to, instead of concentration we will use Pc, the pressure. Okay, pressure of C raised to the power C, okay, small c, Pd raised to the power D upon Pa raised to the power A, and so on. So this equation becomes this. So this is the equilibrium equation. And when we consider, when all the species are gases, सारे species अगर gases में है, so we will consider the pressure. Okay, and here Pa, Pb, Pc, and Pd all are pressure of A, B, and C and D at equilibrium. Okay, but this is at equilibrium. Clear?
Yes.
Now you can write. Just try to write on by yourself. आप यहाँ से भी check देख सकते हो, but try to just do it by yourself. Okay, from here you can write down the derivation. Written, everyone?
Yeah, ma'am.
Okay. So the next topic is relationship between Kp and Kc. Okay, Kp is the constant, yeah, constant at pressure. When we talk about the pressure, so that is the constant term. And what is Kc? Kc is the equilibrium constant. Okay, concentration. Whenever we just talk about the concentration, so we use this constant term Kc. Now let's see let's derive a relationship between the Kp and Kc. Okay, so we know that PV, okay, by the ideal gas equation, PV equals to nRT. Okay, so P will be equals to N upon V RT into RT. So here, this is what is the number of moles upon volume. What is this? This is concentration. Okay, concentration, which type of concentration? Molarity. So can we write P is equals to concentration into RT? Yes, we can. Okay, because this molarity is nothing, it's just a concentration. So we can use concentration for that. And upon V, the number of moles per unit volume is the molarity, and molarity is concentration. So concentration into RT. Okay, so for example, like PA, if I just talk about the PA, okay, basically what we are going to do, let's give it an overview. So PA, we will consider this equation. Okay, and we will derive PA, PB, PC and PD. PA, PB, PC and PD का कुछ formula हम derive करेंगे, and we will substitute these in this equation number 1. Okay, now for PA, what will be PA? The concentration, which concentration? The A concentration. Concentration of A into RT. Okay, let it be A. Suppose let it be A equation. Similarly, for other gases also, PB is equals to concentration of V into RT. Okay, and this is let it be equation number B. Let it be equation number B. Okay, next is P. Basically, you can consider this equation A, which is in gas, plus B, which is in again gas. Okay, so again, this is in equilibrium, forward reaction and backward reaction. Okay, it will give you C, again in gas, and D, which is in gas. So you can consider this general equation. So PC will be concentration of C, okay, into RT. Let it be small c equation. Similarly, for PD also, you can write concentration of D into RT. Okay, now it's very simple. Just substitute A, the value of A, B, C, and D in equation number 1. In equation number 1. And what is equation number 1? Kp is equals to Pc raised to the power C, okay, Pd raised to the power D upon Pa raised to the power A and Pb raised to the power. Okay, now now substitute Pc की वैल्यू क्या थी? Concentration of C raised to the power RT whole C. Okay, whole raised to the power C. Similarly, PD value, concentration of D, okay, into RT raised to the power D upon concentration of A, okay, RT and raised to the power A. Concentration of B, RT raised to the power B. Okay, now let it be. Suppose this is B, this is your second equation. Okay, now see what we are going to do. How we can write. Let's take this RT common. You can take RT सब में common है, right? So can we write this C raised to the power C multiplied by D raised to the power D. A, concentration of A raised to the power A multiplied by concentration of B raised to the power B. Okay, and what it becomes? This is RT. Okay, when you know very well, when the base is same and the power is different, so you can write like this: RT, base is same, power is different, so power get add up because all, both are in multiplication. RT and RT both are in multiplication, and base is same and the powers is different. So according to the exponential rule, we can write RT as a common and C plus D. Okay, in the denominator also we can write RT raised to the power A plus B. A plus. Okay, now, okay, there is a little bit of space. Okay, let me minimize my writing size. Okay, now see. So what you can see, what is this? How, which law of exponent we can apply here? You can see when the power, suppose this is 10, okay, this is again 10. Okay, the base is same and they are divided from. Okay, and the powers are different. So what we are going to do, we just write down 10 and the powers got subtracted, x minus 1. Okay, so we will apply this law of exponent and we can write this equation in this way. Concentration of C, okay, multiplied by concentration of D raised to the power D, A, concentration of A, multiplied by B, concentration raised to multiplied by this RT, commonly log, okay, and this C plus D minus A plus B. Okay, now let's observe this one. Let's observe this. This is very interesting. You can see C plus D. What is a small c and a small d here? And this is small a, small b. So let's see this. See the general equation. Sorry, general equation of ये ले लो. AA, BB, CC. Okay, just add the stoichiometric coefficient. Now check it. This is C, small c and small d. They are the number of moles of the product side. ये क्या है products? Okay, the products के number of moles. Small c and small d. And what about the A and B? The number of moles of A and B. This is the for the reactant, right? So can we? What will be the NP? Sorry, here we will talk about the NR, the number of reactant, the number of moles of reactant side. So you will add these two, right? A plus B को add करोगे. What is this? A plus B is nothing. Is the number of moles, the number of moles of reactant. Okay, the number of moles of A, capital A is small a, right? And the number of moles of B is this B. So when you add these two, you will get the number of moles of the reactant side. Okay, all the reactant side. This is the reactant side. Reactants क्या A है और B है. So you will add these two. The number of moles of these two you will add up, and this will be given as NR, the number of moles of the reactant. And what about this NP? You will represent it by NP, number of moles of product side. So it will be C plus D. Okay, C plus D. Now you got C plus D. What is this? NP, number of moles of product. And what is this? Number of product of reactant. So number of moles of product minus number of moles of reactant. Can we write this as number of delta N, the change in the number of moles of gases, because we are just talking about the gases. So can we write delta Ng is equals to Np minus Nr? Okay, so the change in the number of moles of gases. Product, number of moles of product minus number of moles of reactant. Okay, now see this. ये कुछ देखा देखा सा लग रहा है, this equation? Yes, see concentration. Here you are just seeing the concentration term. So what is this? See this. See this equation. This is equilibrium equation. Yes, Zunaira? Do you have any doubt, bache?
No, ma'am.
So this is equilibrium equation, right? Kc is equals to concentration of C raised to the power C. So can we substitute this equilibrium equation by Kc, right? We can. What is Kc? This is Kc. This whole thing, this is what? This is Kc, right? So we can write, I'm just continuing here. Okay, I'm writing. So Kp is equals to, okay, this Kp is equals to this whole thing. You will just replace this by using Kc because this is equals to Kc. This is an equilibrium equation. So Kp is equals to Kc multiplied by your RT. Okay, and how you will write this? This is Np minus Nr. So what is Np minus Nr? Delta Ng. What is this? Delta Ng. So you will write raised to the power delta N Ng. This is the fourth equation. This is the fourth equation. And that is the relationship between, this is the, you can show like this. This is the relationship between Kp and Kc. Kp is equals to Kc multiplied by RT raised to the power delta Ng. Okay, we will use this in the numerical part. So this, yeah, this equation is important. This formula is very important. Okay, so just remember this formula, just memorize this, and you can write down like here, like after this class, just after confusion, no, what is delta Ng? So delta Ng is the number of moles of gases, and it is the number of moles of gases of product. All should be in gases form. Okay, all species, whether it's a reactant or product, all should be in gaseous form. So number of moles of gases, okay, of product minus Ng of reactant. That is delta Ng. That is delta Ng. Okay, now you can write down. Okay, just derive the relation. Is there any doubt? Is it clear, this derivation?
Yeah, ma'am.
Okay, what about others? Is it clear?
Yes, ma'am.
Yes, ma'am.
Aisha, Neha, Aman, Zunaira, clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, now you can note down. Just note down and inform me. Okay, I will stop it here and we will continue in the next. And please make sure to submit your homework. आप homework ही submit नहीं करोगे, then how I can get to know that आपको समझ में आया topic या there is any doubt. Please submit your homework.